Hello students, so let us continue with electrochemistry. So last topic that we discussed was how molar conductivity varies for a strong and weak electrolyte, and we saw molar conductivity increases steadily on dilution for a strong electrolyte, while for a weak electrolyte we saw yes initially it was increasing slowly, then a rapid increase for a weak electrolyte, because degree of ionization is increases on dilution for a weak electrolyte. So that's the two type of graph that we discussed in the previous class. So it is observed that for a strong electrolyte we can have an equation to find the molar conductivity. That is for a strong electrolyte, for a strong electrolyte. For a strong electrolyte, we have an equation lambda m, which is equal to lambda m0 minus a root c. This is the equation. Lambda m is equal to lambda m0 minus a root c, where lambda m is the molar conductivity. Lambda m is the molar conductivity. Molar conductivity of a strong electrolyte at a particular concentration, and lambda m0 is the molar conductivity at infinite dilution, or we will say limiting molar conductivity. Then A is a constant. A is a constant related to the nature of the electrolyte. A is a constant related to the nature of electrolyte. This A value you can determine. I can tell you how it is. And now A value is found to be constant for a particular electrolyte. For example, NaCl. Look at the charge of cation and anion. This is +1 and -1, right? So this is now one type of an electrolyte where it's a 1-1 type. I will say charge is 1-1. While now CaCl2, while the charge of calcium is +2 and for chlorine is -1. So I can say this is a 2-1 type electrolyte. Another one NgSO4, where now magnesium is +2, sulfate is -2. So this is a 2-2 type electrolyte. So depending on the nature of the electrolyte, A value varies. A is a constant, but it depends on the nature of the electrolyte. That's how you can see the A value is coming. Similarly, C, as we see C is the concentration of electrolyte. Always understand when we talking about discussing about dilution, with respect to dilution, how the molar conductivity varies with the dilution, we always connecting with the concentration, because decrease in concentration means you are increasing the amount of the solvent, or I will say dilution increases. Decrease in concentration, increase in dilution. That's the way you have to think. Now let us think about a graph. What's the graph it is? Now this is the point. Now let us, if you plot a graph between lambda m versus root c, you can see this is an equation for a straight line, where this is y, this is m, this is x, this is c. Y equal to mx plus c. Such a format where you can see minus sign is there, which means it will be a negative slope. So let us draw a graph between lambda m versus root c. For a strong electrolyte, you're getting a graph like this, which is a straight line with a negative slope. Then you can extrapolate it. If you extrapolate to the y-axis, then you're actually getting a y-intercept that is nothing but lambda m0. It's a lambda m0, and you're getting a slope that is which is equal to minus a. That's the slope that you're going to get. And now if you plot lambda m versus root c, You're getting a straight line with a negative slope. So from the slope value, you're going to get the value of A, where I said A depends on the nature of the electrolyte. So this is the point you can remember related to the strong electrolyte. For a strong electrolyte, we can find the molar conductivity at infinite dilution, because now if you extrapolate the graph to the y-axis, which means concentration is 0. Concentration 0 means you have to imagine that is our infinite dilution, or limiting molar conductivity value can be obtained for a strong electrolyte. For a weak electrolyte, the problem is graph is increasing like this, it's going up, it's not meeting with the y-axis. That why at a very high dilution, I will say infinite dilution, for a weak electrolytes, it's not possible to find the molar conductivity. So that's the point. We can extend with the previous class. Now let us discuss what is the degree of dissociation of a weak electrolyte. If you compare the molar conductivity of a strong electrolyte and weak electrolyte, you can see strong electrolytes always having higher molar conductivity value, while weak electrolyte have a lesser molar conductivity value. That's simply because of the less degree of dissociation in the case of a weak electrolyte. So if more number of ions are dissociated, which means molar conductivity will be definitely higher. That's how we saw when you increase the dilution, the molar conductivity of weak electrolyte is increasing, and at infinite dilution, the molar conductivity value reaches to the very high value, and also the degree of ionization become fully they fully ionize at infinite dilution only. That way, at moderate concentration, the degree of ionization of a weak electrolyte is very less. That too, I can give a value to correctly compare. For a weak electrolyte like acetic acid, the formula is CH3COOH. It found that it has a degree of dissociation is less than 5%. That's very less value. More than 95% remaining as undissociated. While now for a strong electrolyte like sodium chloride, HCl, etc., they found to be more nearly 100% dissociated. That's the difference will bring when you're talking about a weak electrolyte and a strong electrolyte. So let us now have a value how to find the degree of dissociation. This we discussed in the previous class. Please go through that, where alpha is the degree of dissociation, which is equal to, now we have a value lambda m divided by lambda 0 m. In the previous class we saw an equation for alpha, where alpha is the number of molecules dissociated divided by total number of molecules. This equation we saw previously. Now we can express the degree of dissociation in terms of molar conductivity and limiting molar conductivity. Lambda 0 m is the limiting molar conductivity. So if you have lambda m value, if you have lambda 0 m value, then you can find the degree of dissociation by taking the ratio between these two. Lambda m divided by lambda 0 m will give you alpha, or degree of dissociation. Or I am representing lambda MC. Lambda MC means molar conductivity at a particular concentration, and a lambda M0, what that 0 suggests, it is molar conductivity at infinite dilution. So that's the way you can find the degree of dissociation of a weak electrolyte. Most of the cases this value going to be very important. Again, in another section it will come. So understand what is degree of dissociation is all about. Yes, just when you're talking about molar conductivity, similarly the equivalent conductivity also varies. Please remember that molar conductivity increases with dilution that we saw for a strong and weak electrolyte. Similarly, the case of equivalent conductivity, because the difference between an equivalent conductivity and molar conductivity is we're talking about 1 mole of an electrolyte in a molar conductivity, while we're talking about 1 equivalent of an electrolyte in a equivalent conductivity. So how the molar conductivity varies with the dilution? Similarly, The equivalent conductivity also varies with the dilution. Please keep in that mind. Now more often than not we are using molar conductivity rather than equivalent conductivity. That why this equivalent conductivity not coming in terms that much as we expected in the case of molar conductivity. So let us discuss another important point that we can discuss: ionic conductivity. Ionic conductivity. I'm sorry, ion conductivity. Ion conductivity. Talking about who is responsible for the conductivity, the answer is ions. No, the presence of ions in the solution makes the solution electrolytic solution makes it conducting, which means if you talk about an ionic compound, there will be cation, there will be anion. It is observed that they independently can contribute to the molar conductivity. So that is very important. The point related to this how much conductivity is offered by each ion, talking about cation and anion independently at infinite dilution. That what here we talking about in ion conductivity. So now let us have an example for this to get a clear idea. Talking about one of the electrolyte, KCl is one of the electrolyte having limiting molar conductivity, that I can write lambda m0. Lambda m0 value that is equal to 130. Remember the unit as well, it will be ohm inverse. Ohm inverse is Siemann centimeter square. Centimeter square per mole is there. I am only discussing this part, where NaCl, which is equal to 108.9 Siemann centimeter inverse. So this is the case centimeter square. So sorry, it is centimeter inverse is actually conductivity. So it will be centimeter square. Centimeter square. Siemann centimeter square mole inverse. That's a real unit. So let me talking about potassium chloride and sodium chloride. We can see the molar conductivity value at infinite dilution is 130, while sodium chloride is 108.9. So what's the change you observe here now? Anion is same, but cation varies. Cation KCl having higher molar conductivity value compared to sodium chloride. Please keep in that mind. Now talking about another electrolyte, let me discuss KNO3. Potassium nitrate and sodium nitrate. Let me take another type of electrolyte like this, where the values are 126.3, and here unit also should be there, and 105.2. Now having look at this value, what are the point you can get here here the change is anion is same, potassium and sodium, how much they contribute to the molar conductivity, that what we can get from this value. Similarly here again, cation and anion are, cation is potassium, anion is sodium, but anion is changed, this time nitrate. So you can get a real idea about how much cation like potassium and sodium contributing to the molar conductivity. Look at here anion is same and cation is K plus and Na plus. Here anion is same, that is NO3 minus another anion. So your cation is same, K plus and Na plus. But now you can see a change in molar conductivity, that is KCl is 130, KNO3 is 126.3. That means keeping a cation constant, anion varies definitely, there you can see a change in molar conductivity. Keeping anion same and changing cation means again there is a change in molar conductivity. So what's the point you can get? Yes, now both cation and anion are contributing to the molar conductivity. That's the first point you can have. Now let us take the difference between the molar conductivity of KCl and NaCl. Now here anion is constant, and taking the difference between KNO3 and NO3, an interesting point is coming. If you take the difference, take the difference between two, you actually getting a molar conductivity that is 21.1. 21.1. Here also you take the difference between these two, it is again 21.1. That means the difference in molar conductivity of KCl and NaCl is 21.1. Similarly for KNO3 and NaNO3 it is 21.1. So what's the point you can get? So that means even though the anion we varies, we saw change in molar conductivity, which is suggests is independent, which is the anion is present. Here it is chloride ion, here it is nitrate ion. So independent, which is the anion present, a cation independently contributing to the molar conductivity. Similarly, anion independently contributing to the molar conductivity. So that's the case. Let me explain one by one. Here look at this. Anion, cation is same, anion is different. You saw difference in molar conductivity. Here anion is same, cation is different. You saw different molar conductivity, which means anion and cation both plays an important part in molar conductivity. That's the first point. Second point, whether in which compound it is, what kind of a compound it is, whether it's depend, that doesn't depends. Now when you're talking about infinite dilution, always remember we are talking about molar conductivity at infinite dilution. So limiting molar conductivity or molar conductivity at infinite dilution, you saw both cation and anion independently contributing to the molar conductivity value. So that why the difference between these two and these two, even though they are different electrolytes, having a same value, that is 21.1. That's how a famous law that is arised, that is we call Kohlrausch's law. Kohlrausch's law also we can call Kohlrausch's law of independent migration of ions. So what is Kohlrausch's law is all about? Kohlrausch's law saying that molar conductivity at infinite dilution is the sum of the molar conductivity of cation and anion. Both cation and anion independently contributing to the molar conductivity when you're talking about at infinite dilution. So let us define first molar conductivity. Molar conductivity at infinite dilution is the sum of molar conductivity of cation and anion. That means anion contributing its own part to the molar conductivity, cation playing its own part in molar conductivity. You take the sum, you're getting the molar conductivity of an electrolyte at infinite dilution. For example, let us give an example. Generally, you can say lambda m0 means molar conductivity at infinite dilution is the limiting molar conductivity of cation plus limiting molar conductivity of anion at infinite dilution. Where now what is x and y? You imagine electrolyte AX BY, electrolyte AX BY. Then how many A is there, how many B is there? That was coming as a stoichiometry here. So lambda m0 molar conductivity at infinite dilution is the sum of molar conductivity of cation and anion. So independently they have a contribution. So let us know give some example. Lambda m0 of NaCl. How what you can write? NaCl is equal to no lambda plus, talking about lambda m0, that is Na plus lambda m0 Cl minus lambda m0 Na plus lambda m0 Cl minus. This is the molar conductivity of sodium chloride at infinite dilution. Now lambda m0 of another electrolyte, this time aluminium sulfate, the formula has to be Al2SO4 thrice, because aluminium plus 3 charge, sulfate is minus 2. So if you interchange it, the formula of aluminium sulfate will be Al2SO4 thrice. So now look at the molar conductivity value. It will be 2 into lambda m0 Al3 plus here how many sulfate? 3 into lambda m0 SO4 2 minus. This is the value we can have for a aluminum sulfate. So what is the value for molar conductivity at infinite dilution for aluminum sulfate? It is 2 aluminum atom is there, 2 lambda m0 Al3 plus 3 lambda m0 SO4 2 minus. This is the way you can find the molar conductivity of an electrolyte at infinite dilution. This is what Kohlrausch's law is all about, because now at the infinite dilution each cation and anion independently contributing to the molar conductivity. Now let us discuss the applications. What are the applications of Kohlrausch's law? Kohlrausch's law have different application. Applications of Kohlrausch's law. First one, you can find the molar conductivity of a weak electrolyte at infinite dilution. You can find molar conductivity of weak electrolyte at infinite dilution. One second. Please go through it. Okay, so we saw molar conductivity of a weak electrolyte is very difficult to determine. Now we plot that graph. We saw it's not easy. At infinite dilution is difficult, but now using Kohlrausch's law, you can find the molar conductivity of an electrolyte, of a weak electrolyte at infinite dilution. How it's possible? Let us now explain through an example. You want to find the molar conductivity of CH3COOH, that is acetic acid for you. We know acetic acid is a weak electrolyte. So how can you find the molar conductivity of a weak electrolyte like acetic acid? We know now what will be the molar. How can you find the molar conductivity? It will be lambda m of CH3COO minus, that is acetate ion, plus lambda m0 of H plus. Both cation and anion are contributing. So lambda m0 acetate ion plus lambda m0 H plus. So contribution from both cation and anion. So this is how you can find it, right? But now how it's possible, let us check. Now we can have the value of molar conductivity of a molar conductivity of a strong electrolyte like HCl. You can have molar conductivity of an electrolyte at infinite dilution of HCl. That you can easily find because it's a strong electrolyte. So you can have this value lambda m0 of H plus lambda m0 Cl minus. This will be the molar conductivity of HCl at infinite dilution. This will be the equation. Let it be put now 1. Now we know another an electrolyte like it is no, let it be sodium acetate lambda m0 CH3COONA lambda m of CH3CON, that is no sodium acetate. Sodium acetate is a strong electrolyte, so we can have lambda m0 CH3COO minus plus lambda m0 Na plus. Let it be equation 2. Now, for a strong electrolyte, we know molar conductivity at infinite dilution can be determined. That we already discussed. So, for an HCl, C3CONA, they are strong electrolytes. Now, having this value, you can calculate the molar conductivity of acetic acid as well. Look at this. We want now summation of molar conductivity of acetate ion and molar conductivity of H plus ion. If you have that value, that's enough. So now here also you can see H plus is there and CH3CO minus is there. But now in the problem is Cl minus and Na plus is also there. But now we know molar conductivity of NaCl, sodium chloride, is a strong electrolyte. It can also contribute to the molar conductivity. So lambda m0 of Na plus lambda m0 Na plus lambda m0 Cl minus. Let it be equation 3. So equation 1, equation 2, equation 3, we have 3 equations. Now you just imagine you are now summing, taking summation of 1 and 2 and you put minus 3. Let's see what's happening. If you sum 1 and 2, you will getting lambda m of H plus, that is required here, lambda m0 CH3CO minus, that is required here, and also Cl minus and Na plus is also coming. That, but now if you minus with the equation 3, where no lambda Na plus and lambda Cl minus is also coming, which means no the Na plus and Cl minus will be cancelled if you minus with the equation 3. So net effect 1 plus 2 plus minus 3, what are you going to get? It is the lambda m0 H plus plus lambda m0 CH3CO minus value, summation of acetate ion and H plus ion at infinite dilution. That what we want, right? For a weak electrolyte, now we know at infinite dilution the molar conductivity will be at infinite dilution is summation of molar conductivity of acetate ion at infinite dilution plus molar conductivity of H plus ion at infinite dilution. That's the way we know the molar conductivity of acetic acid will be, which is a weak electrolyte. But now if you apply Kohlrausch's law, you can see that if you have the values of molar conductivity of a strong electrolyte like HCl and CH3CONA, sodium acetate, and NaCl, you can still find the molar conductivity of a weak electrolyte like acetic acid. So that's another important one of the first application of Kohlrausch's law. Talking about second application, calculation of degree of dissociation of a weak electrolyte. Degree of dissociation of weak electrolyte. Now weak electrolyte like acetic acid, still you can find the molar degree of dissociation by alpha is equal to lambda m divided by lambda m0. This is the equation. for not a particular concentration. Lambda MC is the molar conductivity of a weak electrolyte, and lambda M0 is the molar conductivity at infinite dilution. If you have these two values, you can find the degree of dissociation. But now we have to find the molar conductivity at infinite dilution using the application that I just shown before. No, you have to find first molar conductivity of weak electrolyte at infinite dilution. That value first you have to extract. Then lambda M0, which is the molar conductivity at a particular concentration. If you have these two values, you can find the degree of dissociation of a weak electrolyte. So that also possible. Another applications of Kohlrausch's law. Now it's coming from how you can find the molar conductivity of a weak electrolyte at infinite dilution, because we want lambda M0 of weak electrolyte. That I just show how we can find it using the values of molar conductivity at infinite dilution of a strong electrolytes. You can find the molar conductivity at infinite dilution of a weak electrolyte. After finding that value, lambda MC divided by lambda M0 will give you degree of dissociation of a weak electrolyte. Another application, talking about third application, determination of solubilities and solubilities products. Determination of solubility and solubility products of a sparingly soluble salt. We know some of the salt now easily dissolves in water. Some of the salts are now very less dissolves in water. Such salt now we will call sparingly soluble salt, where no solubility is very less in water. So now, how can you find the solubility and solubility product using now by the application of Kohlrausch's law. So here we know we have a value. We know lambda molar conductivity is equal to conductivity into 1000 divided by molarity. If you're talking about now this molar conductivity of an electrolyte in terms of Siemens centimeter square mole inverse. If you express in that unit, we have a value lambda m is equal to K. What is K? K is actually kappa. Okay, kappa into 1000 divided by m, where K is the conductivity. K is the conductivity. This we already saw in the previous lectures. Please go through it. And m is the molarity. Molarity. Now this is the equation we have, which means now if the number of ions is higher, definitely molarity will be higher. So here you can replace molarity in terms of instead of molarity you can put solubility. Where now what do you mean by solubility is now the concentration of ions. It's nothing but the concentration of both cation and anion. So if you have the solubility value, how much concentration of cation is there, how much concentration of anion is there, that again now you can correlate with the molarity, or no, instead of molarity you can put this solubility value, S value. So now if we have lambda m is this, now just imagine we are talking about molar conductivity at infinite dilution. So instead of lambda m0 you can put lambda m is equal to lambda mc. Instead of lambda mc you can put lambda m0, which is equal to kappa into 1000 divided by S. So if you are provided with lambda m0 value, that is molar conductivity at infinite dilution, you can find the solubility. S is equal to, consider we are talking about at infinite dilution. So S is equal to K kappa into 1000 divided by lambda m0. Using this equation, you can find the solubility, where S stands for solubility. Okay, S stands for solubility value. S is the solubility. Again, now if you look at the unit, you will understand what is S is. It's nothing but now S we express in mole per liter. That's nothing but concentration of a particular ion. So no, that's how you can find the now if you have S value. Now you can find the S value if we have molar conductivity at infinite dilution. Now let me take one example in terms of silver chloride is one of the example for a sparingly soluble salt. So molar conductivity at infinite dilution of AgCl will be lambda m0 Ag plus lambda m0 Cl minus. So now talking about now the molar conductivity at infinite dilution of silver chloride. Now if you want the value of solubility, let me express the solubility of Ag plus, which is equal to, you can express Ag plus into Cl minus. That will be product of concentration of ions. No, it's not S. Let it be S and S. This is concentration of Ag plus I express in terms of S. Concentration of Cl minus I express in terms of S. So if you have these two values, you can find the solubility product as well. Ksp will be the product of concentration of the cation and anion. Okay, when you're talking about solubility product, you have to think about saturated solution. So maximum amount of solute is dissolved. Now we're talking about solubility product is the product of concentration of ions. Okay, at saturated solution. So we express Ag plus in terms of solubility. This is nothing but S is the concentration of Ag plus in mole per liter and now concentration of Cl minus in mole per liter. So what will be the value of Ksp, that is solubility product, which is equal to S square. So let me back to the point. So if we have the molar conductivity of a sparingly soluble salt at infinite dilution, you can first find the solubility. How? Solubility will be equal to kappa into thousands divided by lambda m0. That is, you need molar conductivity at infinite dilution value and the conductivity value. If you have both two, you can find first solubility. First you can find solubility. If you have solubility, then you have an equation for a solubility product, which is nothing but the product of concentration of ions. Here Ag plus ion into Cl minus ion. Express the concentration of Ag plus ion in terms of solubility. So it will be S into S. So it will be S square. So how can you find Ksp? Root of square of solubility will give you the solubility products. Now if you have molar mass of AgCl, molar mass of AgCl is, now it is 143.5 gram per mole. So if you have this value, you can now express the solubility in terms of gram per liter. So multiply, solubility of HCl, solubility of AgCl, you can express in terms of gram per liter. That is if you have solubility value in mole per liter, multiply by its molar mass, gram per mole. Okay, so what will happen? Now mole will cancel. Now you actually getting an answer gram per liter. So you can express still the solubility in gram per liter as well. Now what you need to do? The solubility is expressed in mole per liter. So multiplied by the molar mass will give you solubility in gram per liter. So depending on the question, sometimes you need to express either in mole per liter or in gram per liter. So that's the third application we saw. If you have molar conductivity at infinite dilution value, if you have conductivity value, you can find the solubility of a sparingly soluble salt. After finding the solubility, you can find the solubility product of a sparingly soluble salt. Now the final application, determination of ionic product of water. Determination of ionic product of water. Ionic product of water, how can you express? Kw is equal to concentration of H plus into concentration of OH minus. This is the ionic product of water. Kw, we represent ionic product of water. Here we know water ionizes very less. Water if water easily ionizes means then it will be highly conducting. Pure water will be conducting. But now we saw pure water pure water without any presence of ions now is a poor conductor of electricity, which means they show poor conductivity, which means how can you find the concentration of H plus and OH minus? We saw a small amount of H plus and OH minus is there. We talking about water. Yes, they existing as ions at a very low concentration. So if you have the value of H plus, if you have a value of OH minus, concentration of OH minus, you can find the ionic product of water as well. So all you need to know the value of molar conductivity at infinite dilution. This is something now you can find lambda m0 of water will be equal to lambda m of H plus at infinite dilution plus lambda m of OH minus at infinite dilution. That now using Kohlrausch's law you can find it. You select the suitable electrolyte, you can easily find the summation of molar conductivity of H plus and OH minus that you can find. It is observed that they have a independent value like for an H plus it is 349.8. Now talking about unit express ohm inverse centimeter square plus 198.5 ohm inverse centimeter square. That's the value of molar conductivity of OH minus at infinite dilution. So take the sum, you will get 548.3 ohm inverse centimeter square. This is the value of molar conductivity of water at infinite dilution. You have to imagine some ionization is there. You have to imagine molar conductivity at infinite dilution, H plus and OH minus definitely contribute. So that's the value of molar conductivity of water at infinite dilution. Now you can find the value of conductivity as well. If you talk about conductivity, it will be 5.54 into 10 raised to minus 8. 10 raised to minus 8 ohm inverse centimeter inverse. This is the value of conductivity. When you talk about conductivity, we are talking about a unit volume. What is the conductance offered by all the ions per unit volume? You can say 1 centimeter cube. Within that 1 centimeter cube, what is the conductance offered? So that what conductivity value will give you, and molar conductivity at infinite dilution you can find this. You can find like this using application of Kohlrausch's law. Now we know this is conductivity is the case for a unit volume, and this is now molar conductivity talking about whole volume. So now simply lambda m0 of H2O will be nothing but talking about conductivity into volume. If you have total volume, then conductivity into volume will give you molar conductivity of water at infinite dilution. So now still you can find now volume or conductivity or now molar conductivity of water if you have any two value using this equation. Molar conductivity of water is equal to kappa into V. Please keep in that mind. Then now let us go to back to the point now how you can find the concentration of H plus and OH minus. Now you have this value, this molar, you have the conductivity value and we have the molar conductivity value, right? So 5.54 into 10 raised to minus 8 divided by 548.3. So what these values are about? This is the conductivity of of water at a unit volume. Here this is the molar conductivity of water at infinite dilution. So dividing these two, you actually getting the concentration of ions in a unit volume. Talking about 1 centimeter cube, you getting the value. If you divide it, you will get a value that is now coming around 1.01 into 10 raised to minus 10 mole. This is the actually the concentration of both cation and anion. We are talking about 1 mole of water. The concentration will be like this. Now you imagine they are ionized at infinite dilution. Then the concentration of H plus and OH minus both will be 1.01 into 10 raised to minus 10 mole. How can you find? If you have the conductivity value, if you have molar conductivity value, divide it, now take the ratio, you will getting the number of the concentration of H plus ion, which is equal to 1.01 into 10 raised to minus 10 mole, and the concentration of OH minus ion, which is equal to 1.01 into 10 raised to minus 10 mole. Now this is talking about within 1 centimeter cube volume. Generally we express not in centimeter cube, we will express in liter. So how can you convert this into liter? Multiplying by, because 1000 centimeter cube is equal to 1 liter, or which is equivalent to 1 decimeter cube. 1 decimeter cube is equal to 1 liter, which is equivalent to 1000 centimeter cube. So now you are talking about the number of moles of water or number of moles of H plus ion or OH minus ion in 1 decimeter cube. How can you find? Multiply by this value into 1000. 1.01 into 10 raised to minus 10 into 1000. This time you are actually getting the concentration of H plus ion and the concentration of OH minus ion in mole per decimeter cube. Here it was mole per centimeter cube. So here if you multiply, you will get 1.01 into 10 raised to minus 7 mole per decimeter cube. This is the value of concentration of H plus. Now similarly, concentration of OH minus ion, same value, 1.01 into 10 raised to minus 7 mole per decimeter cube. So these two values we have. Now you got concentration of H plus, concentration of OH minus. If you have these two values, multiply both to get the ionic product of water, because we saw ionic product of water is Kw, which is equal to product of concentration of H plus into concentration of OH minus, which is equal to 1.01 into 10 raised to minus 7 into 1.01 into 10 raised to minus 7. If you multiply it, you will get in a value around 1.02 into 10 raised to minus 14 mole into mole, mole square, decimeter cube into 2, that is decimeter raised to minus 6. This is the case at 25 degrees Celsius. At temperature is also there at our normal temperature. So this is the way you can find the molar ionic product of water. What's the step? Ionic product of water is nothing but product of concentration of H plus and OH minus. So now one point you look at the value. Any product of what is very less. What's the concentration of H plus is gone. 10 raised to minus 7, which is very low concentration. Concentration of H plus ion is very low. Concentration of OH minus is very low. Which means water rarely very small. We will say very small extent it ionizes. So the point is how can you find H plus, how can you find OH minus? If you have that value, you can find it. So all we can find now using Kohlrausch's law, you can find the molar conductivity at infinite dilution. Similarly, you can find the molar conductivity at a particular unit volume. So molar conductivity per unit volume divided by molar conductivity at infinite dilution of water, you are actually getting the concentration of both H plus ion and OH minus ion per unit volume. If you have that value, we are talking about centimeter cube. You can convert it into per liter or per decimeter cube. I can by multiplying by 1000. So actually getting a value which is now 1.01 into 10 raised to minus 7 is the concentration of S plus ion in not talking about 1 liter per liter, mole per liter or mole per decimeter cube. And talking about concentration of OH minus is also same because if they ionizes equally. Both concentration of H plus ion and OH minus ion will be same. So if you have these two value, multiply both to get the ionic product of water. All these four application thanks to Kohlrausch's law, because by using Kohlrausch's law we actually found these all thing. First one starting with the molar conductivity of a weak electrolyte can be determined. That is the first application. Then molar conductivity, sorry. Then for a degree of dissociation of a weak electrolyte, that also can be determined. Then the next one is solubility and solubility product also can be determined. And the final application, ionic product of water also can be determined. So please go through it and now if any doubt is there, you can ask. Okay, thanks for listening. Thank you.